Alrighty, howdy folks. Uh, let's look at chapter 6, section 2. This is about trigonometry of right triangles. Trigonometry of right triangles. Hey, for the first time, we have bumped into this term trigonometry. Right, last section we were just talking about angle measures and things like that. Now let's get to the real thing. For this, let's start off with this old concept that you knew from geometry about something called similar triangles. What was that concept? Let's say I showed you two triangles. Uh, would you call them similar triangles? Yeah, man, they kind of have the same shape, right? They do. But there's something more. Um, On what grounds do we call them as similar triangles? This is what must happen. If you pick a certain angle of this triangle, let's say the first one, and there must be another angle in the bigger triangle, the other triangle, which must be equal to this one. So it turns out in this case, angle A is exactly equal to angle P. They are both the same. Not only that, angle B is equal to angle Q. Now, if two of these angles are equal, that's it. The third angles must be equal. Would you agree with that? Angle C must be equal to R. How come, man? Well, that's because the moment two of these angles are given, the third angle is automatically determined by 180 minus A plus B. Right? It's guaranteed. Now, if A plus B is the same as P plus Q, 180 minus A plus B must be 180 minus P plus Q, that is R. So C must be equal to R. Anyway, what's important for similar triangles is the corresponding angles be equal. Cool. All right, so what did I say? The two triangles A and PQ are similar triangles because angle A equals angle P, angle B equals angle Q, angle C equals angle R, just like I said. Okay. Now, let me ask you this. Does this mean the line segments are equal? Is AB equal to PQ? Is BC equal to QR? No. No, not necessarily. It's possible, but it need not be so. Oh, isn't that interesting? The angles are equal, the corresponding angles are equal, but the corresponding sides are not equal. Yeah, that's entirely possible. Now, do you remember what you call the triangles if not only are the angles equal, but also the sides? Well, you call them as congruent triangles. Here we do not have congruent triangles necessarily, we just have similar triangles. Cool. Okay. When we do have similar triangles, do you remember anything interesting about them? There must be something that must happen, right? You've already established the two triangles are similar. Now, what is something that must happen for those things? I'll give you a hint. Ratio. Ratio of what? The ratio of the line segments. Some of those ratios must be exactly the same. I'll tell you in just a second what those ratios are. But before that, notice this lowercase a, b, and c. We have uppercase a, b, and c, which indicate the vertices of this triangle. And each of those angles is given by the same uppercase letter. So if we look at this angle BAC, that's the same as uppercase A. ABC is uppercase B, and so on. Then what's up with this lowercase? Well, it turns out the convention is the side opposite of an angle is the lowercase letter. For example, if you look at this angle A, the side opposite of that is this side, right? And because this angle is A, this side is said to have a measure of lowercase a. Similarly, across from B, opposite of this angle B, is lowercase b. That segment is said to have a length of b. And C this way, because it's opposite of C. Okay, that's the convention, and that's what I have adopted even for PQR. Cool. Now let's get to this ratio of sides that I was talking about. When we have these two triangles being similar, the ratios must be, the ratio of the corresponding sides is the same. I'm sorry about that. Ratio of the corresponding sides is the same. What do I mean by that? That means if you pick A, side A on this triangle, what is the corresponding side on this one? P. So A over P, we can form a ratio. And that is going to be exactly the same as the ratio of the other corresponding sides. For example, B is one side on triangle ABC, and the corresponding side on PQR triangle is lowercase q. Cool. So B over Q is the other ratio, and A over P must be B over Q. And the last thing that we are left with is C over R, and that's got to be equal to C over R. Cool. Excuse me. So once we have this understanding, there's something else I can say. From A over P equals B over Q equals C over R, just focus on the first two things. A over P equals B over Q. Just for a second, ignore the C over R, okay? From this, could I cross multiply and divide accordingly so that I can now, based on this, say A over B is P over Q? Are you with me on this one? A over P right now is B over Q. Could I cross multiply so that I have AQ equals PB, but then divide both sides by B? So I would have A over B is equal to P over Q. Similarly, A over C is equal to P over R. And if we look at these two things, from that we can say B over C is equal to Q over R. So from this set of equalities, we can actually come up with three other sets of equalities. A over B equals P over Q, and A over C is equal to P over R, and so on. And that is the key. Here is the idea. Now consider the two right triangles, OAB and OPQ. Okay, OAB, OPQ. These are the two right triangles. Question: are OAB and OPQ similar triangles? Right? What a good question, right? Are OAB and OPQ similar triangles? If you said yes, awesome. The question is, on what grounds? I don't know, man. They kind of look the same. Okay, I'll kind of accept that. But can you be a bit more rigorous? Can you kind of prove? Ooh, the big word, prove. Can you prove that they are actually similar triangles? Well, how, if you haven't figured it out, let me direct you back to this statement. The two triangles are similar triangles because the corresponding angles of one triangle, the corresponding angles of the two triangles are equal. What does that mean? Is that something that happens in OAB and OPQ? Let's look. Is there a 90-degree angle here? Yeah, angle B is 90 degrees. Is there a 90-degree angle here? Yeah, angle Q is 90 degrees. Cool. So these two angles are the corresponding angles and they are equal. Nice. What about this angle? Theta. Well, that is theta, and that angle, is that an angle of the triangle OAB, or is that the angle of the triangle OPQ? Both. Oh, you mean theta is the same angle whether you look at it as OAB's angle or OPQ's angle? Yeah, it is. So that means theta is the same. That angle is the same for the two triangles. Already we established that the 90-degree angles are the same. The moment you have two angles equal of two triangles, the third angles must be the same. That's what I argued earlier. So all the three corresponding angles are equal. Therefore, these two triangles, these two right triangles are similar. Cool? Did you get it? Wonderful. Now, where do we go from there? Where we go from there is this concept. Oh, you mean the ratios are the same? Yeah. What ratios? These these ratios. I'm picking only on one side. I'll pick stuff from one triangle, that is AB over OB. AB over OB is equal to, the corresponding sides are PQ over OQ. So equals PQ over OQ. Similarly, AB over OA is PQ over OP, and so on. Now, this is the root of all trigonometry. These ratios being the same is what drove the concept of trigonometry. And what mathematicians decided is, if this is the case that these ratios are always the same for right triangles, let's call these ratios by special names. Right? And so they said, all right, in general, ladies and gentlemen, this is what's going to happen. They said, if you have a right triangle like this, and say this angle is theta, of course one angle is 90 degrees, then we will call this side, the biggest side, always as the hypotenuse, right? Isn't that what we've always done? Call the longest side as the hypotenuse. Okay, and what should we call the other two legs of the right triangle? They said, okay, check this out. You got this, you're looking at this angle theta, right? And is there a side that is opposite of that angle? Yeah, this side. Cool. What is that? This side is opposite of this angle theta. So guess what? Call it the opposite side. Hypotenuse is always the longest side. That's easy to figure out in any right triangle. The only thing is, what is opposite? It depends on the angle. The angle theta is, this is where you're looking at this is where you put your theta and looking at this angle. Then the one opposite of the side opposite of that is the opposite side. Cool. What about this other horizontal leg? What should we call that? And that is called adjacent side, because it is adjacent to the angle theta. One of the adjacent sides is the hypotenuse, so that name is already given. So the only thing is, what's the other adjacent side? Oh, that's the other one, the bottom leg. So they said, anytime you see a triangle, right triangle, recognize these three quantities based on the angle where you put. Now, please pay attention to this. Could I have put the theta over here? Yeah. Well, in that case, can you assume this? Let's say theta is actually this one. Is the hypotenuse going to be different? No, hypotenuse is always the longest side. So hypotenuse, regardless of theta being here or here, is going to be the same. Cool. Is this going to be adjacent? No, man. No. If you got theta over here, opposite to that theta is this side, and so this is going to become the opposite side. Oh, okay, then the other non-hypotenuse adjacent side, this must be the adjacent. Right? Things switch. That's all you need to know. So opposite, hypotenuse, and adjacent. Nice. And then they said, you know that ratio of opposite over hypotenuse? That is what we call as sine theta, and typically written as sin theta. No, I did not commit any sin. Ooh, joke. So sine theta written as sin theta, but completely spelled out it is sine theta. And sine theta is opposite over hypotenuse. That's a special name given to that ratio. Similarly, cosine theta is the name given to the ratio adjacent over hypotenuse. And tangent theta is what opposite over adjacent is. Cool? There are three more. Sine theta, cosine theta, tangent theta. And cosecant theta, written as CSC theta, is hypotenuse over opposite. Secant theta is hypotenuse over adjacent. And cotangent theta is adjacent over opposite. You have got to memorize these. You must. Okay? And there is a mnemonic that actually helps you remember at least the first three. And it's called SOHCAHTOA. SOHCAHTOA. The way you're supposed to use this is S, sine, O is opposite, H is hypotenuse, sine opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite over adjacent. Cool? That's the mnemonic people use in order to remember, wait a minute, is cosine adjacent over hypotenuse? Well, SOHCAHTOA, sine opposite over hypotenuse, CAH, cosine adjacent over hypotenuse, TOA, tangent opposite over adjacent. That's it. Cool? And then, what's up with these other ones? Cosecant theta, that is hypotenuse over opposite. Wait a minute, didn't we already have opposite? Oh, we had opposite over hypotenuse. Ah, interesting. This is apparently hypotenuse over opposite. What does that mean? This is opposite over hypotenuse. This seems to be flipped version of it. What do I mean by flipped version of it? That means it is the reciprocal of that. In other words, cosecant theta is the reciprocal of sine theta. Reciprocal? I don't know what the word means, man. Oh, it simply means 1 over that. So cosecant theta is nothing but 1 over sine theta. Where did we get that from? Because apparently by definition cosecant theta is hypotenuse over opposite. But we see that this is nothing but 1 over opposite over hypotenuse, where opposite over hypotenuse is sine theta. So 1 over sine theta is what cosecant theta is. Cool? Now, notice this one. Secant theta is hypotenuse over adjacent. Does that look like the reciprocal of something? Yeah, man. Cosine theta is adjacent over hypotenuse. This is hypotenuse over adjacent. So secant theta is 1 over cosine theta, man. Awesome. Exactly. You are absolutely right. Cool. Cotangent theta, similarly, is the reciprocal of tangent theta. So once you know SOHCAHTOA, and then you know which one is the reciprocal of which, you're done. You know all the trig ratios. And we will be using this over and over and over again, probably for the rest of our lives. At least the college life. Especially if you're an engineer, or a mathematician, or a physics major. Chemistry? Maybe. Alright, with that, let's do some silly problems. Find all the six trigonometric ratios for the triangle shown. Okay, so we got a right triangle, and we are given 6 and 8, and that angle is theta. And we need to find all the trig ratios. That means sine theta, cosine theta, tangent theta, secant theta, cosecant theta, and cotangent theta. Alright, let's get busy. First, we will recognize that with respect to the given theta, we know what? Opposite is equal to. Can we identify all the things? Which one is which? Which the opposite hypotenuse adjacent? Which one is which? Opposite. Opposite of what? Opposite of the theta. So, would you agree the opposite of theta is this line, this segment, 6? So opposite is 6. We know that. What do we call this? This 8. Is that the hypotenuse? No, man. Hypotenuse is the longest side, the biggest one. Awesome. Very good. I'm impressed. Right? So adjacent is 8 and hypotenuse. Question mark. Ooh, I like that. We don't know what the hypotenuse is, but they are asking us to find all the trig ratios. Sine theta, we know, is opposite over hypotenuse. But how can I find the sine theta if I don't know the hypotenuse, man? Right? Yeah, you can find it, man. You know how? You remember that good old Greek guy? What? Greek guy. What Greek guy, man? The guy whose name starts with a P. You mean Pythagoras guy. Yep. Pythagoras theorem, we know that hypotenuse square is opposite square plus adjacent square. Right? Okay. So hypotenuse square equals opposite square plus adjacent square. That means hypotenuse is square root of opposite square plus adjacent square. Is that right? Did I say it right? Is it true that if hypotenuse squares this square plus that square, hypotenuse itself should be square root of it? Strictly speaking, in this case, we should say plus or minus. Okay, plus or minus square root of opposite square plus adjacent square. But I didn't write the negative because in this case, we know that that side will have a positive number. That length of this segment is not going to be negative. So that's why I ignored the negative and simply took the positive and said hypotenuse is simply positive square root of opposite square plus adjacent square. Now, plug and chug. Opposite is 6, adjacent is 8, so 6 square plus 8 square. 6 square is 36, 8 square is 64, 36 plus 64, when you add, you get 100. Square root of 100 is 10. And so the hypotenuse, even though they never gave it to us, we figured out because we are smart people. And so we figured out the hypotenuse to be 10. Now everything is piece of cake. Plug and chug. Recall the formula. Sine, so, S-O-H, Sine opposite over hypotenuse. Sine theta is, do not just say sine, you must give the argument of sine. Argument, what? Argument. I'm not fighting with you, man. No, 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 no. Argument means sine of something. That something is called the argument. So you cannot say sine. Doesn't make any sense. Sine theta makes sense because sine of that angle theta is, in this case, opposite over hypotenuse of our given triangle, and we know opposite and hypotenuse to be 6 and 10, so 6 over 10, you reduce it, 3/5 you get. Cosine, recall, ka, so ka, C-A-H. So cosine is adjacent over hypotenuse, and that's going to be 4 over 5, 8 over 10, which reduces to 4 over 5. Tangent theta, opposite over adjacent. 6 over 8 is 3/4. Cosecant is a reciprocal of sine theta, so 5/3. I didn't do that. I should have, I could have, I would have. But another way is hypotenuse over opposite, so 5/3. Secant theta, hypotenuse over adjacent, 5/4. Cosecant theta, what? I goofed. That ain't no cosecant, dummy. Sorry about that. That's cotangent theta. Let me save that. I'm sorry for my mistake. I bet while making this, I just simply copied this thing and didn't change it. I hate making mistakes like that. Anyway, where were we? Yeah, let's look at another problem. Ooh. Find the 6 trigonometric ratios here. What's the standard procedure? We need all the sides. So with this theta, we know opposite is 5.
Sure.
She's going crazy. Opposite is 5. Adjacent is, don't know. Hypotenuse is 8. Cool. Can we call the Greek guy again and figure out adjacent? Yeah. Hypotenuse square is opposite square plus adjacent square. So adjacent square must be hypotenuse square minus the opposite square. I simply subtracted the opposite square from both sides. That's all I did. And flipped sides. Simple algebra. You get it, right? And so adjacent itself must be plus or minus square root of that, but we'll take only the positive. So just simply square root of hypotenuse square minus opposite square. And so plug and chug. Hypotenuse is 8, opposite is 5, and this turns out to be square root of 39. What? You mean you won't necessarily end up with nice numbers like 5, 6, 7, 8 like that, man? Yeah, square root of 39 is perfectly valid. So 64 minus 25 is 39, right? 39, 44, 64, yeah. Huh. For a minute I thought maybe should that have been 49 to make it 7? Nah, that is square root of 39. Okay, so sine theta, opposite over hypotenuse, cosine theta, adjacent over hypotenuse. Just, you know the drill, folks. I'm not going to insult your intelligence. You guys are way too smart. We get it, man, you say, right? Cool. Fine, simple problems. What else? Trigonometric ratios of specific angles. I like this. I really, really like this. And I have a feeling so will you. What's the idea here? Right now, we just got sine theta. What's theta? Theta is some angle. What angle? I don't know, some angle. Okay, give me some specific number, man. Come on. And that's where this trigonometric ratios of specific angles comes up. We're going to learn about sine, cosine, and all these things, trigonometric ratios for 45 degrees. What is sine of 45 degrees? Apparently we'll be able to find out exactly what that number is going to be, right? How do we do that? For that, we need to consider an isosceles right triangle as shown. Isosceles, what a word, man. What's an isosceles triangle? Well, it's one of those triangles where two sides are equal. A third side need not be equal. If it is, that's a different story, but there is no imposition on the third side. But if it is an isosceles triangle, then there is an imposition that two of the triangle sides better be equal. And in this case, let's say the two legs are equal. Obviously, the leg cannot be equal to the hypotenuse. Hypotenuse is a completely different one. It's the biggest one. So, let's say the two sides are A and A. Will Mr. Pythagoras come and help us with finding the hypotenuse? Yeah, he's a good guy. He's on our side. He'll tell us exactly what it was going to be. So hypotenuse is square root of opposite square plus adjacent square, square root of a square plus a square, which is square root of 2a square. And that's equal to square root of 2 times the quantity a? Yeah. Do you agree that square root of p times q is square root of p times square root of q? What? Let me repeat that. Is square root of p times q, is that equal to square root of p times square root of q? Yeah. Okay, if that is the case, can I look at square root of 2a square and say that must be square root of 2 times square root of a square? Yeah. So square root of 2 is this. Square root of a square, isn't that equal to a? Plus or minus a, but here we are looking at only positive. So a? Yeah, that's how I got that. No mystery to it. Cool? Okay, where do we go from here? Oh, we know now the hypotenuse apparently. Cool, just like in the last problem. Let's try to find out, can we find a measure of any there's some more work left for us. We got the sides, but we don't know anything about the angle. Especially, of course, we know the right angle, but what about the other two angles? Do we know what those angles should be? Can we find the measure of any non-right angle of the triangle? That means it's that question is asking, hey, can you figure out what this angle is or that angle is? Well, yeah, I think there are ways to finding that out. Recall that for any isosceles triangle, the base angles are equal. The base angles? What in the world is that? Well, it just so happens if these sides, this bottom segment and the vertical segment, those are the two equal sides, then at the base of this, not at the apex, so this point would be the apex of that, whereas these two, this point and this would be base. So those base angles must be equal. Isn't that cool? Because this is an isosceles triangle with these two sides being equal, the base angles, this angle and this angle must be the same. Let's say that is theta. This also must be theta. Okay, can we figure out what theta must be based on that? I don't know. Yeah, come on, think about it. Do you understand my question? We got this to be 90 degrees, great. And this is theta, and that is also theta. Can you tell me what theta ought to be? Do you remember? The sum of the internal angles of a triangle is equal to 180 degrees, of which one of them is 90 degrees. So the other two must add up to 90. So this angle theta, that angle theta should add up to 90. Theta plus theta is 90. 2 theta is 90. Theta must be 45. Right? That's the idea. Simple, folks. So theta plus 90 must be 180. 2 theta plus 90 is 180. Subtract 90 from both sides. Divide both sides by 2 and you get theta to be 45 degrees. Aha! So that angle is 45 degrees and even the other one is 45 degrees. We don't need to mark that other angle. With this 45 degrees, let's now figure out all our ratios, trig ratios, sine, cosine, tangent, secant, cosecant, and cotangent, and all that. Opposite over hypotenuse becomes a over square root of 2a. That's the hypotenuse. A square root of 2. A and a, we can divide both the top and the bottom by a and you get 1. And in the bottom we get square root of 2. So 1 over square root of 2. Sine of 45 degrees is square root of 2 over 2. You remember, if you wrote 1 over square root of 2, that's okay with me. Somehow mathematicians seem to have a big problem or big issue with, oh, you can't have a radical in the bottom, man. I don't know why. Why? Because, in olden days, you couldn't divide like that. That was in olden days. We are in a modern age. We are in the 21st century. Who cares? We're not using log tables to figure out divisions. Right? So, folks, but just in case you bump into some mathematician who has a big issue with something like this, let's learn to do what they talk about. When you have 1 over square root of 2, you can multiply both the top and the bottom by square root of 2. When you do, you get 1 times square root of 2, which is square root of 2, and the bottom square root of 2 times square root of 2 is 2. Right? So, in essence, sine of 45 degrees is actually square root of 2 over 2. Man, for the first time, you have found the trig ratio of a particular angle. From now on, like bragging rights, hey dude, check this out. Do you know what sine of 45 degrees is? You're like, I don't know, man, what is it? And you can go, that's square root of 2 over 2. And cosine of 45 degrees, similar idea, adjacent over hypotenuse, turns out to be 1 over square root of 2, and that's square root of 2 over 2. What? You mean sine of 45 degrees is the same as cosine of 45 degrees? Yep. And it's equal to square root of 2 over 2. Cool. What is tangent of 45 degrees? Well, tangent is opposite over adjacent, a over a. What? A over a. That's equal to 1. Right? Any number divided by itself is equal to 1, right? Right? 5 divided by 5 is 1. 7 divided by 7 is 1. 9 divided by 9 is 1. Negative 976 divided by negative 976 is 1. The 0 divided by 0 is... I hope you didn't go with the 0 divided by 0, that's equal to 1, man. No, man. 0 divided by 0 is undefined. It is not equal to 1, so don't fall into the trap. But here, we are confident that a is not equal to 0, and that's why when we look at a over a, we can say that is in fact equal to 1. But we couldn't say it if a were to be 0. In that case, we would have had 0 over 0, which ain't equal to 1. Cool? All right. Cosecant 45 is a root 2 over a. Turns out to be square root of 2. Cool. Secant 45 is also square root of 2. And cotangent of 45 degrees is 1. Cool. So for 45 degrees, we figured out the trig ratios. Now let's look at, let's try to find for 60 degrees and 30 degrees. For this, we got to do something like this. We need to look at an equilateral triangle. What is an equilateral triangle? All three sides are equal. Are all three angles equal? Yep. And what is that? What should the internal angles, what should each internal angle be in an equilateral triangle? Right? And the smart people in the class are going, either give the answer right away or think through, wait a minute, you said all three angles must be equal. So if I were to think of that each angle to be theta, then we have theta, 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 three of them. So 3 theta, when I add them up, I get theta plus theta is 3 theta. Hey, but when you add, you should get 180 degrees. So 3 theta is 180 degrees. So theta divided by 3, 60 degrees. You mean each of these angles must be 60 degrees? Yep, you are a genius. Cool. And in addition, let's say we drop a perpendicular bisector to this guy that will pass through the vertex. That's there's a theorem for it and all that we can prove. If I try to perpendicularly bisect the bottom segment, then automatically that perpendicular bisector passes through the apex, the other vertex, and so we have a over 2 and a over 2. This is guaranteed to be 90 degrees because I said perpendicularly bisect. And when we do, we know this angle to be 60 degrees. And what else did I do? Yeah, this angle is 60 degrees. Maybe I do have that, but I didn't put it right here. Okay, maybe next I'll put it. So this angle is 60 degrees. This angle is also 60 degrees. And this whole angle is 60 degrees. But if we were to look at only that part, how much would that be? Is that the same as this part? Yep, this is not only a perpendicular bisector of this line segment, it also bisects that angle, meaning cuts it into 2 equal parts. So the 60 degrees has been split into 2 equal angles. So that means each angle must be 30 degrees. That's the key. So this is 60 degrees, that is the 30 degrees. And so if we say adjacent is a over 2, opposite is this guy, hypotenuse is a. We are looking at this triangle. That's what I have. Hypotenuse is a, adjacent, opposite is what did I do? I goofed. I'm sorry folks, I'm an idiot. This ain't no adjacent, man, that's opposite. And this ain't no way out. That's the one that is adjacent. Okay, now we are in business. Let me save this guy. I apologize for wasting your time. Let's get here. So opposite is hypotenuse square, the square root of hypotenuse square minus adjacent square. For this angle 60 degrees, this would be the adjacent and that's the opposite. So a over 2 yeah, so sine of 60 degrees is opposite over hypotenuse, opposite square root of 3 over 2 over a, right? For 60 degrees, this is the opposite over the hypotenuse. You get square root of 3 over 2. Cosine of 60 is adjacent over hypotenuse, a over 2 over a, 1/2. tangent of 60 is opposite over adjacent. The square root of 3 over 2 over a, or the a over 2, and that reduces to square root of 3. Cool. And cosecant is the reciprocal of this. I could have done that, 2 over square root of 3, or multiply both the top and the bottom by square root of 3, we get 2 square root of 3 over 3. Secant 60 is just reciprocal of 1/2 is 2, and cotangent 60 is the reciprocal of square root of 3, which is 1 over square root of 3, or we can write that as square root of 3 over 3. Cool? So for 60 degrees, we know all the trig ratios. Now, for sine 30, we will look at this angle, and opposite is now a over 2, adjacent is square root of 3 over 2a, and hypotenuse is still a. We use those and we get sine 30 to be 1/2, cosine 30 to be square root of 3 over 2, tangent theta is square root of 3 over 3, tangent theta is 1 over 2, yeah, 1 over 2 over square root of 3, okay, yeah, that's right, is square root of 3 over 3. Cosecant is 2, the reciprocal of sine theta. This is 2 square root of 3 over 3. You know what I'm doing here, right? I'm going through this a little quicker because I'm hoping this is all obvious. If not, just pause the video and figure out those things for yourselves and check, verify whether or not you get the same answers as I do here. All right, folks, I think we are done with this section. Thank you.